Hello everyone. Today's notes are from section 9.1 on momentum and impulse. So our learning targets today are to define both momentum and impulse, to review Newton's first law, which we talked about in class today also, and to link the law to momentum and impulse, which is our new topic. So our questions are, what is momentum and when would objects have that? What is impulse? And when do objects experience that? And how are all these things related? Momentum, impulse, and Newton's first law. All right, so let's go ahead and get started. We're going to define momentum. So momentum is, whoops, that's in the wrong place. Here we go. The tendency of a moving object to keep moving. And so you would say that a bowling ball rolling down a bowling alley is going to keep on rolling, right? It has momentum. A car driving off a cliff, oh, that's a bad example, isn't it? But anyway, the car would continue to go off the cliff because it has momentum. If you're running and you see something you need to stop, right? You have momentum. Your body wants to keep running. You have to work to stop. Okay. Because momentum is a directional thing, we say it's a vector quantity. Right? So that means that direction is going to be important. All right. So you get all those terms back in your head. So our formula to figure out momentum, first of all, P stands for momentum. I don't know why, it just does. I'm sure there's a reason somewhere back in history. So P is momentum. And the momentum is equal to the mass of the thing times the velocity of the thing, right? Straightforward formula, that's the kind that we like. And if you think about it, that makes sense, right? In order to have momentum, you have to have some mass, right? There has to be something that's moving, and you need to know how fast you're going. The more mass you have, the more momentum you have. The more velocity, the more momentum. You can have mass, but no velocity, and then you don't have any momentum. All right, what would we label this? Well, these are weird units, but we take the units for mass, which are kilograms. We take the units for velocity, which are meters per second, and we put those together, and so our units here are kilogram times meters per second. All right, so think about all those things for a minute. Momentum, the tendency of a moving object to keep moving. The direction is going to be really important here, right? You can be moving in a positive or a negative direction. And the more mass you have, the more momentum, the more velocity, the more momentum. All right, so let's check this out and see if we can figure out whether or not these things have momentum. So the first one is a dump truck moving at 15 meters per second. So we have to ask ourselves some questions here. So does this thing have mass? Well, it's a dump truck, so yes. Does it have velocity? Well, it told me up here that it's moving at 15 meters per second, so yes. So does the thing have momentum? Well, it has mass, it has velocity, so it must have momentum, so yes. All right, see how we're going to do this? All right, B. A canoe paddled at 5.6 meters per second. Does this thing have velocity? Well, let's see. Does it have mass? Yes. Does it have velocity? Yes. Does it have momentum? Yes. Right, it's got to have mass and velocity. Okay, this one is your turn. That bowling ball is sitting there at rest. Okay, so stop the recording. Fill in your answer. Does that bowling ball have momentum? Okay, good for you. All right, so then we're going to move on and talk about impulse. What is impulse? Impulse is a force that causes a change in the motion of an object, or a change in the momentum. Again, this is going to be a vector quantity because direction is important here. So I've got my thing, my whatever, my object, it's moving along, and I can push it from behind, right? That's a force, and that would make it speed up. Or I could apply the force in front of the object, and that would make it slow down. So direction's really important here. All right, how do we calculate this? Well, I is for impulse. That makes more sense, doesn't it? The impulse is equal to a force. Okay, well, that makes sense because it's in the definition, times the time. So you can have a big force and a small time, or you can have a small force and a big time, right? If you don't have any force, then of course you don't have any impulse. Okay, so both those things are necessary. How do we label this one? Well, same kind of thing as we did with momentum. Force is in newtons, time is in seconds. So we call these Newton seconds. I know, that's kind of weird. All right, so same thing here. Is the object experiencing an impulse? Well, let's find out. Okay, so these cars are colliding. Let's see, is there a force present? Well, they ran into each other, so yes. Did it take some time? Everything takes time, so yes. So is there an impulse here? Yes. Force and time. Okay. Part B, is this swimmer experiencing an impulse? Well, let's see. Is there time? Well, there's always time. So, yes. Is there a force? Well, it says the swimmer is moving at 1.5 meters per second. It doesn't say anything about that motion changing, so I'm going to say no. There's no force here. So, is there an impulse? Nope. No force, no impulse. Okay? So you have to have both the force and the time. All right, your turn. A golfer hitting a ball. Is that ball experiencing an impulse? So stop the recording, fill in your answer, decide, is that ball going to experience an impulse? All right, good for you. So now we need to review Newton's first law here. I'll bet you can already figure out how these things are related, but let's go ahead and do it just in case. So remember, Newton's first law, whoa, too far, my bad. Here we go. Newton's first law says, an object in motion. Oh, an object in motion. Doesn't that sound like momentum? Right? That's momentum. Will stay in motion so once it has momentum, it's going to keep its momentum until, do you remember what happens after the until? Acted upon by an outside what? Yep, an outside force. And we know that another word for that is impulse. Okay? So that's how these things are related to each other. An object has momentum as long as it's moving, and it will continue to have momentum until that outside force, that impulse, acts on it. And I can cause the motion to speed up, I can cause it to slow down, I can cause it to change direction, and I can cause it to stop, right? All of those things would be a change in the momentum. So how would we write this? Well, we would take this whole idea, recognizing that these two things are going to be equal to each other. We can say that impulse is a change in momentum. If I wanted to write that as a formula, I would say impulse is equal to the change in momentum. Remember that triangle? That's delta, and that means a change in. Impulse is equal to the change in momentum. Or I could write it, and this is more useful, Ft, right? That's impulse, is equal to mv, that's momentum. So the impulse is equal to the change in momentum. All right? So pause for a minute, go back, make sure that you are okay with all of those terms and how they're related to each other, and then we'll do the example problems. Okay. So I'm going to rewrite my formulas up here because you know me, I like to have them all right where I can access them. So momentum, mass times velocity, impulse, force times time. And then I know that the impulse is equal to the change in momentum. Whoops. So Ft equals mv. All right, here we go. So it says a compact car with a mass of 725 kilograms is moving at 32 meters per second toward the east. And this time we're going to call east the positive direction. Remember, I told you direction was important. So what do I know? I know the mass is 725 kilograms. I know the velocity is 32 meters per second east. Okay, and A says calculate the momentum of the car. So I need to find momentum, all right? So P is equal to mv. So I know it's going to be 725 times 32 meters per second. And that is going to give me a momentum. Hold on, where's my calculator? Here we go. Of 23,200. That's a big number, but that's okay. Kilogram meters per second. Why is that such a big number? Well, because the mass of things is big, right? And the bigger something is, the more momentum it has. So that all makes sense. So it would surprise me if it were a small number. Okay? All right. So that's part A. Part B says, what direction is the momentum acting? Well, let's see. If the velocity is east, and mass, of course, mass isn't directional. Mass doesn't have any velocity. So if the velocity is east, then the momentum is east. So that was easy, right? The momentum has to be the same direction as the velocity. Okay, part C. Part C says a second car with a mass of 2,175 kilograms has the same velocity as the car, but is headed west. Calculate the momentum and the direction of the second car. Okay, so what have I done? Well, my mass is going to be different now. The new mass is 2,175 kilograms. The velocity is the same, 32 meters per second, but the direction is now west instead of east, and I need to find the new momentum. All right, what do you think? Is this momentum going to be bigger or smaller? Yeah, you're right. It should be bigger, right? Why is it going to be bigger? Yep, because my mass is bigger. So I'm going to have 2175 times 32. My calculator here, that's going to be 69,600 kilogram meters per second. And I have to say the direction. And so because this time I'm going west, this momentum is to the west. All right, look that over if you need to. What did we change? We changed the size and the direction of the car, which also changed the size and direction of my momentum. Okay, example number 2. The driver of the compact car in the above problem braked hard for 2 seconds, applying a force of 5,100 newtons. All right, so what do we know? Let's see, how about green? This time, we know that it's the same car, so it's going to be the compact car's mass, so it's 725 kilograms. We know that we used the brakes for 2 seconds. We know that there was a force of 5,100 newtons involved. All right, and part A says calculate the impulse on the car. Okay, so impulse is force times time. Oh, I guess I didn't need the mass, did I? So I'm going to have 5,100 times 2. I feel like I should be able to do that in my head. Let's see. So 10,200 These are newtons times seconds because my force is in newtons and my time is in seconds. All right, so there I calculated the impulse. And then it says for part B, what direction is the impulse acting? Okay, so let's think about this. If the car, and remember it's the car from the first part of the problem, so if the car is going east, right, with its velocity, and it slows down, then that means that the force must be in the opposite direction to make the velocity slow down. So if this was east, then my force has to be west, so that means that my impulse is to the west because the car slowed down. Does that make sense to you? Okay. So let's take a look. Did we answer our questions? What is momentum? Momentum is the tendency of a moving object to keep moving. Objects have momentum as long as they have mass and velocity. What's impulse? Impulse is the force that changes the motion. When do objects experience an impulse? Whenever they have a force over a time. And how are these things related to Newton's first law? Well, it's just another way of saying Newton's first law, right? An object in motion has momentum. It's going to stay in motion until it's acted upon by an outside force. That's the impulse. Okay. So you have a problem to do down here. You are going to calculate the momentum of this snowmobile twice, and then you are going to calculate the amount of force used. So that's a little bit different than our example, but I have confidence that you can do it. Make sure that you write down any questions you have. We can talk about them in class next time, and I will see you next time.